Hello, kids, and welcome back to another one episode. It's not an episode, another course in business statistics. So it's the second week, and you're going to learn new stuff. So I'm back for another one. This week we're going to talk about application areas of statistics, both within business area and other areas that it's applied to. And we're going to make an introduction to data, which is the core of the statistics, the main input of the statistics discipline. Okay, so let's get started. I'm hoping the sound is better this time. I'm trying to speak louder. I couldn't do anything with the microphone, so I'm going to just hope that it's good. And let's start with a quick summary from last week. So we said that statistics is the science or the art or the technology that processes information, that uses data to find meaningful insight. What we mean by meaningful insight is the insight that lets you help make better decisions. And it does all this stuff when the information is not perfect, when there's uncertainty. So this is a very good thing for the managers, for the decision makers, the business administrators, right? So let's start with the non-business application areas. I could only include a few. There's a lot more, and as long as there's uncertainty, there's statistics over there. We're going to start with psychology. Psychology is one of the sciences that has helped statistics become popular, at least in the last decade or so. Another one is criminology. Criminology and statistics, how does that relate? It relates like this. Criminology is about population, it's about people, and statistics is the science that gathers information from people and helps you make decisions. For example, it's going to help you make understand the behavior of serial killers or whatever. That's what I imagine. And engineering also. Engineering uses lots of statistics, especially as far as I know, electronics uses lots of statistics. And what else? Public health, and related to that, epidemiology and the very popular recent case of pandemiology. What else do we have? We have environmental studies. Statistics help understand the populations and population behaviors of certain types of animals and endangered species and so on. What else? We've got genetics. Genetics also uses lots of statistics. And astronomy. Okay, you have to read a little bit about this because it's too huge. And then there's biology. I couldn't find the interesting enough image for that. In the business area, okay, you have statistics almost in everything. For example, you have statistics in marketing, which helps you understand consumer behavior, consumer structure, and so on. You have statistics in production. You use it to, for example, estimate demand patterns, cost structures, and product prices, and so on. When you talk about prices and estimation, you use it a lot in finance, again, to estimate stock values, returns, interest rates, exchange rates, and blah blah, lots. Operations research uses statistics, and statistics uses operations research. They serve for the same purpose mostly, to help you make decisions based on facts or plausible facts. Big data, data mining, and machine learning, these are very similar. You can add artificial intelligence to it, and they all make up a family that is the new version of statistics, new dimension of statistics. So the classical, earlier or middle-aged statistics now became big data analysis, data mining, machine learning, artificial intelligence, and so on. And economists use econometrics. We statisticians do not say econometrics, we say multivariable or multivariate regression. They are almost the same thing. You will learn some basic regression this semester, and I'm hoping to also show you, at least in a basic level, how to come up with multivariable models, some econometric models or multivariable regression models, critical points in that, and how you can, simply carry out that sort of analysis using a computer program. It's almost incredible to do by hand. But apart from that, I will expect many of the stuff I'm teaching to be done by hand, because you can. Okay, and quality control and reliability. This is almost all about statistics. The numerical portion of quality control and almost all of reliability is pure mathematics, and 90%, 95% based on statistical analysis and statistical concepts. Okay, let's move on. What are you going to see this semester? So I will give you a simple outline of this semester and next semester, and you will have an idea of what you're going to be learning. We're going to start with data. Okay, you're going to learn data types, scales of measurement, scales of data, and organization of data, how you will organize and rewrite data so it is more readable, and related frequency distributions, another simple way of showing data and a simple way of calculating stuff from data. And you're going to learn about graphs, what graphs we have, what do we use them for, which types of statistical information is shown by a certain type of graph, and how you can draw them by hand or by Excel or by some other softwares if we need to. Okay, and based on those, you're going to be learning about data. Of course, I didn't include it here, but another important point is the properties of data. Okay, probably next week, before learning how to organize, how to get frequency distributions and other stuff, after learning types of data and scales of data this week, I'm assuming next week you're going to learn properties of data sets. You will need these properties because it lets you understand if a data set is similar to another one, which is the basis of statistics actually. The rest of the analysis is a way of proving that your estimations are correct. Okay, so we're going to start with data. This is going to be about 1/3 or 1/4 of the semester. Then we're going to move to relationships, not the relationships that you're understanding at the first view. These are the relationships between variables. Say a variable x and a variable y. Are they in? They are not in a relationship. Do they have a relationship? So look at the graph here, for example. It gives you class ranks, underclassmen, upperclassmen. You can think of it as first 2 years in university, and this is the second 2 years in university, third and fourth years. And do you live on campus? As you can see here, 34% of the underclassmen, first 2 year students, live off campus, and 94.3% of them lives on campus. There's got to be something wrong with this. Okay, the proportion is based on columns. So it's 79 to 148. Almost 2/3 of the first 2 year students live on campus, live in the dormitories, and a huge majority of third and fourth year students live off campus, and very few live in the dormitories. I don't know where this data is taken from, but the link is here, so you can follow and try to understand which country that is. this is this kind of information. So looking at the graph here, you may probably try to say, okay, does your years in university have an effect of living in or out of campus? Because the relationship cannot be the other way around. You cannot say, okay, if I pick a random student, the fact that he or she lives on or off the campus, can this information help me estimate whether this student is an underclassman or upperclassman? You cannot infer that way, but you could infer the other way. So if I pick a random upperclassman, do I expect that person to be living on or off campus? So that kind of information. Sometimes these variables could be directly mathematically linked, sometimes they're not. So based on the type of data, we're going to have two types of relationships. We're going to have categorical relationships, which we mostly define by cross-table analysis or contingency analysis, another name for that. And if we have numerical data, numerical information, we generally do correlation and regression analysis. So you're going to learn both of these methodologies. Cross-table analysis is a very simple and easy to teach and easy to understand method, and it takes an hour or so, doesn't take long, but we're going to be spending a lot of time, I guess, in correlation and regression analysis. This is going to take for me to just explain like in 2 weeks, and with the related examples and post-analysis, and maybe adding multivariate regression, which is the same as econometric analysis. This could take up to 4 or 5 weeks, I don't know. And okay, this is how a correlation and regression analysis looks like. This is a graph showing latitude of where the people are living and mortality rates based on skin cancer. Okay, so as you can see, this graph shows as latitude increases, the mortality rate decreases. Do you think there's a relationship here? Can you generalize this as saying, okay, as latitude increases, mortality rate decreases? You probably can. It's not like a strictly increasing function or a strictly decreasing a monotonic function in mathematics, but this is not mathematics, this is statistics. You look at the general look of the data. Okay, so there are exceptions, but a general direction is downwards. How reliable is this? How much can we trust on this? You're going to learn how to infer those. And there's also another issue here. I just noticed that I haven't made a note of it. It's not introduction to data, it's not relationships, it's a third different topic, which is known as goodness of fit. We're going to use it to try to understand whether a given data set follows some certain properties. For example, you're going to learn about some distributions in the near future. You're going to be seeing, maybe exponential distribution or Poisson distribution, or binomial distribution or normal distribution, which is very popular. And these are generalized data shapes. Some certain data which acts in a certain way is sometimes or mostly generalized as a known distribution because it looks very much like that. So some certain parameters, certain variables act like normal distribution. For example, if I put all of you students into an IQ test and obtain your results, it's probably going to follow a normal distribution. If I obtain your weights or your heights, it's probably going to follow a normal distribution. But if I, observe your ages, it's not going to look like a normal distribution. It's going to have some different properties. Okay, so you're going to learn about these. In goodness of it, in the third portion of the semester, we're going to try to understand if some data sets behave in a certain pre-assumed way. Okay, I'm going to show you how to do that. Okay, next semester is going to be all about statistical inference. You're going to learn about sampling distributions, you're going to learn about confidence intervals, you're going to learn hypothesis testing, analysis of variance, the power of the test, and so on. These five basic topics is going to take about 15 weeks. Okay, uh, but of course, you're lucky you have me. You're going to learn them uh, easily. So the regular approach in teaching statistics, as far as I have seen up to this day, is, you know, this is the first year I'm using PowerPoints in statistics. Basically, you know, I pick up my pen, the board marker, and go to the class. Sometimes I take my computer with me to show a couple of stuff, but I teach at the board. Now I'm teaching at the teaching from a PowerPoint that I prepare myself because I have to. You know, what else can you do? So using PowerPoints during the course was a popular approach, and because you do that, you cannot explain everything clearly. So the lecturers generally let students use a formula sheet. Okay, so you take this formula sheet with you to the exam, and you look at it, and you use it whenever you can. I have never let my students use formula sheets. You're going to learn why. Another approach is to memorize the stuff. This is not a teaching method, but this is a method used by students. They try to memorize, but I don't want you to memorize stuff. It's going to be too hard. And please believe me when I say this. You know, 50 to 70% of the formulas that I will be teaching you, I don't know. I don't memorize any of them. I don't remember them when you suddenly ask me. But be it online, which is distance learning, or be it face to face in a classroom, I I remember them as I teach them. Okay, and some lecturers use packages, so you directly jump off to a computer package and you learn how to use it. But this is a risky way of doing things. I could simply take, SPSS or eViews or Minitab or any other statistical software, and first teach you how to use the commands and so on, and then lecture using that. But there's a trouble here, there's a risk here, and that risk is students sometimes may have the chance to get lost clicking buttons, and they don't know what to do. Okay, whenever you click a button, something shows up as the screen here, but if you don't know what this thing is doing, what it means, what information you get out of it, it's nonsense. Okay, it's just some fancy graphs. This happens when I read exam papers, for example. When I used to read, when exams were face to face, I would mark a paper, say 10 or 20 out of 100, and my wife would look at the pages and say, "Oh, this looks like very complex mathematics," and I say, "No, it's gibberish." Okay, the student tried to write everything he knows so that I would think that he knows something or she knows something and award him points. But I don't eat that. Okay, she eats because she's not a statistician or a mathematician. But I look at the paper, 4 pages, front and back, filled with formulas and calculations, and it's zero. There's nothing in it. Okay, this risk is higher when you directly use computer packages. You click buttons, things show up, they look fancy, they look like mathematics or statistics at a complex level, and you say, "Oh, I'm doing this." You're not doing anything. You're not learning anything, and you don't have an idea what you're doing. Okay? I don't want it to be like that. But if you understand the concepts, what they are, why they are used, how they are utilized, then you can click any button you like, because when you look at the buttons, you'll know what it does. Okay? Computer packages only help you in calculation. They don't make you learn things. Okay? If you don't know what you're doing, you don't get anything out of a computer package, be it a statistical package, or be it a 3D modeling program like AutoCAD or whatever. Okay, think of a computer package that you know nothing about in theory and practice. Take it and click buttons, something will happen. But I think you get my point. My approach, I like to tell stories. Okay, I don't write formulas. I tell stories, and these are generally mathematical stories. Okay? Some of you may like it, some of you may not. Some of you may prefer, okay, if we could only use formula sheets. Now you're going to use formula sheets because you're going to have a distance exam. No problem. So this year it's also free. But it's more important to write a formula correctly. It's not more important to write a formula correctly. It's more important to understand what you're doing. Okay, to understand what you're doing, you're lucky you have me. I will tell you stories about what you're learning. I will be able to explain some by stories and not be able to explain some. So this formula you see here, df, degrees of freedom, equals to s1 squared over n1 plus s2 squared over n2 in parentheses squared up divided by blah. This is known as the Behrens-Fisher degrees of freedom. I have never been able to memorize this formula, okay? Because just simply looking at it, I don't remember a story about it. Maybe I could then, I would explain it by a story. But take a look at this formulation here: r square vy ve 1 minus, and these are what vi and ve's are. This looks more complex, right? This one has a story. For example, I will explain it to you so clearly that you won't have to actually memorize these things. If you need to memorize them, you will have formula sheets with you, but basically you will know the story, what happens and what they are and why they are there and so on. So if you show the interest, basic interest that is required for the course, I will make you understand it, okay? No problem. So we're going to start with the data. So this is your first chapter, the first of the 3 chapters. I'll just have a drink of water and okay, let's go on. I've told you that there are types of data. You're going to learn the types of data, the properties of those types of data. You have to learn this because the types of data is directly linked with the type of analysis. You cannot use every type of analysis using every type of data. They are mostly not interchangeable. Okay, so they have a hierarchy. There's hierarchy in data types and there's hierarchy in analysis types, and they fit each other. Alright, so what are these data types? We're going to base our data types on mathematical operators, some basic mathematical operators. Alright, so we're talking about 2 different data types here. One is categorical data. I've talked about this a moment ago, not a moment, but a couple of moments ago. First is the categorical data type, and the second is the numerical data type. So for a moment, think about these. Think about information that springs to mind. So I'm looking around, I see the coat of my son, and it's red. Okay? And the inside of the hood is striped. Red and striped. 2 information types. Are these numerical? They're not. So I made up some based on a fact true categorical information. And what else do I see? I see a black t-shirt. So colors. categorical information. And what else do I see? A photograph, and then I see a larger photograph, and then I see even another larger photograph, all side by side. So this is another information: small, medium-sized, large. Is this numerical? Can you add them up, subtract them, multiply them? No. And what else? But I can use this as a numerical information. I see 3 photographs, right? And I see 6, 7, 8, 9, 10 packs of creams. I don't know what creams they are, toothpaste or something like that. So this is numerical information now. Both of these groups, categorical data and numerical data, are also subdivided to 2 groups each. So the first scales of measurement, or first data type, is nominal scales of measurement, or nominal data. Okay, this is the simplest form and the lowest in the hierarchy. It is based on names. So my name is Onur and your name is Ahmet. So using this information, we cannot do anything. We cannot subtract them, we cannot add them, and we cannot order them. We can do an alphabetical order, but what's an alphabet? Who decides A is first and Z is last? Okay, there's no point, or there's no order in alphabetical order. So we can only say, okay, you're Ahmet, I'm Onur, so our names are different. If you're Onur and I'm Onur, then you can be Onur Kemal or something like that. Alright? So only equals and unequals. If we don't want to be mixed up with each other, as in Atatürk's case, the teacher could say, okay, it's very okay, it's not very kind to change people's names, but that's what happened. I could say, okay, you are Onur Kemal from now, or Onur Can. I don't know. The reason why I'm linking this with the story is to make you remember what nominal scale is. It's names, only equals and unequals. And everybody knows almost that story about Atatürk, so that's why you can link this scales of measurement with that. Names of people, names of things, names of cities, whatever. Alright? Names. The second categorical one is the ordinal scales. Nomine, in Latin it's name. Okay, so I'm a metalhead, so there's a band that I love, which is Venom. They had a song, I think, or an album, in nomine Satanas, in the name of Satan, written in Latin. Nomine is name, so nominal. Ordinal, it comes from order. Okay, so in an ordinal scale, you're able to order the information. Since, as I said, there's a hierarchy between data sets, nominal is the lowest in hierarchy, ordinal is one level higher. Ordinal includes nominal scale, but it also has other properties. What is it? Smaller or larger, smaller or equal, larger or equal. So you can use all the combinations of these mathematical operators here. Ordinal scale can differentiate between equals and unequals, but it can also order stuff. We're going to see examples of that. Let me just quickly tell you about these ones. The rest is numerical. Okay, we have interval and ratio scale. Interval scale is the third in hierarchy. It includes nominal, it includes ordinal. Added to those, you can subtract and add. If you remember, we had it looked like a casual way of giving information and asking information from you in the WhatsApp group. I asked, okay, tomorrow's going to be twice as cold. The temperature's dropping. The reason was that for you to discover the interval scales, the difference between interval and ratio scales. As you know, when you're talking about temperatures, you can sum up or you can subtract. You can say the temperature is dropping 10 degrees tomorrow. Does this make sense? Yes. If you say the temperature is dropping to half, this doesn't make sense, because the 0 in the Celsius scale or the Fahrenheit scale is an artificial 0. It doesn't have a meaning. It's a practical way of moving the data scales from an absolute 0, which is 0 degrees Kelvin, to an understandable position, which is close to the freezing temperature of water, 0 degrees Celsius. What's it in reality? It's like 273 point something Kelvin, or I don't remember the actual name, but that's the fact. And in ratio scales includes nominal, it includes ordinal, it includes interval. Added to that, you can you can multiply and divide. For example, your age could be 22 and my age is 44, so I can easily say I'm twice as older as you. When you're talking to me, are you talking to me? When you're talking to me, be careful, because I'm twice as experienced than you. I've seen lots of things. I've been to everywhere in the world. Okay? Is that a fact? Yes, because age 0 means you're just born or have not been born yet. And any data that has similar type of properties, they're in ratio scales. Like, for example, the number of your siblings, that's ratio scales. Interest rate, that's in ratio scales. And what else? The amount of demand that you face in a given period of time, ratio scales. Your wage, ratio scales. The price of a product, it's ratio scales, and so on. It goes on like that. Okay, so these are the 4 basic data types: nominal, name; ordinal, based on order, you can order ordinal data; interval, it's numerical, but it can be negative, because the 0 is not a meaningful 0, it's not an absolute 0, it's an artificial 0. And the ratio scale is what we understand as real variables, stuff that when you say 0 means there is nothing of it. I have 0 liras in my pocket, that means I have no money. Alright? So since in terms of data, nominal scale is a subset of ordinal scale, and both of those are a subset of interval scales, and all 3 are a subset of ratio scales. That means it's the same case in terms of analysis. What do I mean by this? I mean this: you can have an analysis that is good for a nominal scales. Since ordinal scales include nominal scales, you can use that analysis here. But if there's an analysis good for ratio scales, you cannot use it for nominal scales or ordinal scales. Okay? So the hierarchy in data is also the same in hierarchy of analysis. So, what do we have as nominal scales? Names, place names, names of people, names of places, barcode numbers. Okay, this is a number, right? That's a number. Is it a numerical information? Is it a numerical data? No, because you cannot take 2 barcode numbers and sum them up and find a meaningful barcode number. So you cannot take the barcode number of a shoe and barcode number of a computer, sum them up to find the barcode number of an iron. You iron your clothes, that kind of iron. You cannot do that. You cannot subtract them, you cannot sum them, you cannot even order them. Ordering barcode numbers is like ordering names in an alphabetical order. So this is also nominal. Club names, types of debt. Okay, now debt itself is numerical. Okay, so this is numerical, $16,000. $176,000, $29,900, and so on. This is the numerical part. But the left-hand side is nominal. That's coming from credit cards or from mortgages or loans or student loans or any type of debt. These are nominal scales because there's no order in these. You can order them based on the magnitude of your debt, but you cannot order these in. They don't have an order. Okay, credit card order is not more important than a student loan, or is not less important than a mortgage, or whatever. All right. So there's no order here. This is the left-hand side is nominal. And okay, so what else do we have here? These are percentages of different industries. So construction industry 12%, finance, insurance, real estate 8%. Okay, so this is not Turkey because construction 12% is not, and services 40%. Okay, this doesn't make sense for Turkey, but okay, these percentages here, they're numerical, but the types, they have no order. Okay, these are nominal. Types of industries: retail, services, mining, agriculture, transportation, manufacturing, wholesale, blah blah. Nominal data types. So if you're only interested in the names of these industries, that means you have nominal data in your hand, so you can use only analysis that fits nominal data. Okay? Ordinal scales, okay. First in a race, second in a race, third in a race. This is a race of being Russian, I think. Everybody is Russian, so this guy is more Russian than that one, and or you know, a sport that Russia is very good at. I think this is Winter Olympics or something. Sochi 2014, something I haven't followed. But the places these guys have won are ordinal. Looking at these two guys, you know that this is the first and this is the second. Alright, or maybe this is the second, I don't know. It should have written here. Anyhow, first and second, we know that this guy was faster or stronger or more intelligent, whatever race that was, than this guy. And then this guy is more intelligent or faster or stronger or whatever than this guy. But we don't know how much. Okay? Maybe the time between these two guys is a tenth of a second, and the time between that guy and that guy is an hour. We don't know. We just know that this is the fastest. A little less faster than that, and this is the slowest guy. And all these three guys, if there were other people in the race, are faster than the other ones. Okay? And then you can convert this information to nominal. Medal winners and the other people, non-medal winners. There's no order in those. Maybe you can imply that, okay, these are medal winners, so these are faster. So this could be thought of as an ordinal scale too, maybe, but if we care about having a medal or not having a medal, that's our only concern, then that's nominal scales. Some have, some don't. There's no order there. Okay? So you can convert ordinal data into nominal, but you cannot take the nominal data and convert it into ordinal. You cannot say, okay, these are the medal winners, those are the non-medal winners. Let's now try to estimate the ranks in this race. You don't know who is the first. There are three guys, and one of them is the first, the other is the second, the other is the third, but you don't know. So you cannot convert back. You can convert downwards in a hierarchy, but you cannot convert data upwards in a hierarchy. So, ordinal scales, military ranks. Again, ordinal. Osteman. I was one of those. When I finished, I was one of those. And it goes on like that. Right? And academic ranks. Undergraduate, this is you. Graduate or postgraduate, postdoc, assistant professor, that's me. Okay? Associate professor, full professor, and so on. It goes on like that. Again, you know that this guy has finished undergraduate, and that guy has finished graduate or postgraduate, and that guy has finished all of those. Good. And okay, now, how satisfied are you with the statistics course or purchase, service, and company overall? And there are answers here. You all must have filled out this type of questionnaires before. This is known as a 5-point Likert scale. This is coded as 1, 2, 3, 4, 5. It is converted into a number, but those numbers don't have a meaning. But they can be ordered. But they shouldn't and cannot. They can, but they shouldn't be used as numbers. You shouldn't be summing them up. It's very risky. Suppose I ask you, how satisfied are you with the statistics courses so far? And 50 people say very satisfied, and 50 people say very unsatisfied. And that is 1, that is 5. Okay, if I take an arithmetic mean, if I sum them up and divide to 100, I will find 3. And I could say, okay, on the average, everyone is neutral. Okay, so it's good for me. My average is not below 3. It's not above 3, but okay, who cares? No, half of the people are very satisfied and half of the people are very unsatisfied. So there's a problem here. Okay, I should be taking care of those problems. If it goes 5 4 5 4 5 4 3 4 5 5 4 4 3 and a 2 here and there, and if that is the case, okay, but still I shouldn't be summing them up. I can code these as numbers, but I shouldn't be summing them up. Right. And when you fill out a questionnaire, this is used as an input for analysis. Okay, this is an ordinal data, so you have to do some ordinal data-based analysis to this. And another one. Okay, this is very unreadable, but this is the input data for a AHP analysis. That's known as analytic hierarchy process. All right, and it asks you stuff like that. You have two options. You have to compare them as a person. Apple here and banana here, and if you don't like either of them equally, you say okay, so. And then if you say okay, I prefer banana to apple more, you can go as high as 3, 5, 7, 9, depending on how much you like a banana. But of course, again, that is ordinal information. That is a little incomplete information. So when you choose that, is this because of you like apple but you like banana even more, or you hate apple and you don't like banana much, but you prefer it anyway to apple? It doesn't give this information. So ordinal information is therefore, whenever converted to numerical, doesn't have a meaning. Okay, I want you to think of this about ordinal scales very much, oh very very much, not so much, oh I hate it, that sort of answers, and why you cannot convert them into numerical data. You convert them for analysis purposes, but okay, why you cannot use them as a numerical data? What's the danger there? I want you to think about it, and maybe if you have questions, then we're going to talk about it. Actually, remind me to talk about this in a live session. All right. Why can we not use ordinal scales as real numbers? And so on. Numerical is just numerical. You can think of hundreds of examples for this, and this difference between interval and ratio is simply the existence of a meaningful or an absolute zero. Okay, in a ratio scale there's an absolute zero. In an interval scale you have an arbitrary zero that you choose. For example, let's think of a ratio scale variable and convert it to interval scales. For example, heights of people or weights of people. Okay, I ask everybody their weight, but I ask it like this. Okay, suppose we have Burak in the class. I don't know if we have a Burak, but we have Burak in the class and he's 70 kilos. Then I ask all the boys, because you cannot ask the girls their weights, right? It's not, that's not right. Being a gentleman, you cannot do that. But you can ask the boys their weights, and you can say, okay, give me your weight compared to Burak's. So if you're 75, tell your weight as +5. And if you're 60 kilos, compare yourself to Burak and say -10 kilos, and so on. So we took ratio scale data, 70 kilos, 75 kilos, 60 kilos, those are in ratio scales, and then we convert them into interval scales by setting Burak, who is 70 kilos, as a arbitrary or an artificial 0 point. Then everybody claims their weights as compared to Burak, where 70 is the 0. Okay? So practically you could say any variable that can take negative values should be, or possibly should be, an interval scaled variable. And any variable that cannot take a negative value should be a ratio scaled variable. Think of this, try to come up with different examples, try to find contradictions if you can, and also let's talk about this. Alright? Take this as a simple basic homework to think about. What else do we have? Okay. I've shown this. Okay. I should have shown it here. Since you have hierarchy in data, then you should have hierarchy in parameters and in analysis. Now this is the correct one. I should remember to delete that one after the video. In terms of parameters and analysis, that means a parameters are calculated numbers that show some properties of your data set. Okay, so for example, soon you will learn, but you're going to have a location parameter, for example, or a variation parameter, a dispersion parameter, or whatever. A parameter for interval scale, interval and ratio are together in that, by the way, would also include the information that you get from an ordinal scale, maybe, or is more useful than that one. The main idea is actually usefulness. Being able to use is one thing, and being useful is another thing. You can take a parameter or an analysis that is good for nominal scales, you can apply it to ratio scales, alright? You can do it, but it wouldn't be very effective. The detail you get from that analysis would be too few to get some information out of a ratio scale data. The other way around, you cannot do it. You cannot take the ratio scaled analysis and use it in a nominal scale. That is something you cannot do. The other way around you can do, but you wouldn't be able to receive as much as information out of that analysis. But sometimes this could be the case. You may have a nominal scaled variable and you can have an ratio scaled variable, and you should be using these two variables together in an analysis. Then what will you do? If you choose a ratio, if you choose an analysis that is good for a ratio scale, you wouldn't even be able to calculate the parameter or do the analysis for nominal. So you will use the analysis that is good for the lesser scale, lesser in hierarchy. Okay? So there's no inferiority here, but there's a hierarchy. And so if an analysis method or a parameter is good for ordinal scales, it could also be applied to ratio scales. So you can find the location parameter good for ordinal scales, you can find the same parameter in the ratio scale, no problem. Or if there's an analysis good for ordinal scales, you can apply the same analysis in ratio scales. Why? Because ratio includes the ordinal in it, but not the other way around. So if there's an analysis or a parameter that is good for ratio scales, okay, you cannot apply it to ordinal because this is lesser in hierarchy. That information is too much to be carried out to an ordinal scale and apply. You cannot just simply do that. So in this sense, we talk about governing principles. Okay, what we mean by governing principles is the principles that let you come up with parameters for scales that you're seeing, come up with analysis for the scales that you're seeing. So a nominal scale is the names, and you can only use the principle of culmination or the principle of accumulation, or whatever you want to call it, for the nominal scales. You can only count and get them together in terms of frequency, and that's it. You cannot do anything else with the nominal scales. So if we're interested in names, we're interested in the name Emre, for example. We can only count the students in the class who have names Emre and find the frequency. For example, suppose the pets that you have, we're interested in that, and we count and we find that 5, 10, 12 people have dogs in the class, 7 people have cats, 6 people have goldfish, 3 people have budgies. Budgie is a type of bird, hamsters, 1 lizard, 1 snake, who's that person, and 3 rabbits. Okay, these are names of animals, and we can only accumulate them in terms of frequency. We can culminate them and say, okay, the vast majority of the class is cats and dogs, and say goldfish maybe. And I don't want to visit the people who have lizards and snakes, and so on. Okay, all you can do with the nominal scale is count them, so you can find parameters for nominal scales which are based on counting, and you can apply analysis for nominal scales which are based on counting. You can do all this to ordinal and interval and ratio, but not the other way around. So the only way of finding parameters and coming up with analysis for nominal scales is by counting the values of the data set. All right. Ordinal. The principle for ordinal is dividing points and ratios. I think we're going to spend some time on it, maybe next week. But dividing points and ratios is dividing the frequency of a data set. This is going to become clearer very soon. So suppose this is a frequency graph, okay? This group has that much of frequency, that group has that much of frequency. In fact, it would have been better if I didn't use a continuous case here, but a blocked graph. But anyhow, these are frequencies. So if you divide this frequency graph, number of people or percentage of people, right from here, how many would be left? How many would be right? Or what percent would be on the left? What percent would be on the right? If this is the line of dividing, you could see that 13.6, 15.7, 15.8. The left has 15.8 of the whole group. The right has the remaining proportion. All right. So when we say dividing point, that is a dividing point. And when we're talking about a dividing ratio, that is a dividing ratio. Okay. For ordinal scales, you can use culmination-based parameters and analysis, but they will give you less information than you would like, so it's better to use dividing points and ratios. But again, we generally use either that, so as I said before, cross-table type of analysis, and social scientists would like to use the numerical analysis in the ordinal scale. They believe that it could be done. There are a couple of, not much, but 1 or 2 papers that say, okay, under these types of conditions, it could be used, but I don't like it much. Anyhow, third one, interval and ratio. The numerical scales, the 2 of them, even though interval doesn't have a absolute 0, they are considered together because they are both subject to central gravity. This is the typical Newtonian mathematics that we understand. Okay, this is calculus mathematics. So there's lots of moment functions here. Maybe this is a word you may want to search moment functions. Moment functions around a point. That point would generally be the central gravity point. Okay, so you're going to see very soon that when we're talking about parameters and properties of those data sets, you will be seeing moment functions. So for example, the first moment function around zero, first power moment function around zero will give you the arithmetic mean, while the second moment around the arithmetic mean is going to give you the variance. The third moment around the arithmetic mean will give you another parameter, which is for skewness, and the fourth one is going to give you a parameter based on kurtosis and so on. And you will learn what they are. Don't hurry, but take a look at moment functions basically. Alright. So these are the basic principles. So we have three principles, which means we have three levels of analysis: one for nominal, one for ordinal, and one for numerical. And the critical and important point in statistical analysis is to know what data you're dealing with, what type of analysis fits that kind of data, and what that kind of analysis gives you as information when you complete it. So basically there are two ways of doing statistical analysis. One way of doing it is you look at the data, you understand what type of data you have. So if you know what type of analysis you could apply, you look at the data and you try to ask questions. Okay, in the classical case, you look at the data, you find the analysis that fits it, do the analysis, find the outcomes, and try to make something out of that. A better way is the more scientific and more statistically nice way of doing things is you first ask questions. You try to understand your questions, try to understand what type of analysis will give you answers to those questions, and what type of data will let you make those analyses, and then obtain data regardingly. Okay, this is a better way of doing things. Now these are the classical two ways of doing statistical analysis. Sometimes you just have data and you try to understand or try to find out, okay, what can I do with that data? What information can I get out of it? Sometimes you start by asking questions, better way, decide the related analysis, and obtain the necessary data. Now in the near future, last 20-30 years, as these new emerging methods are more and more used, like machine learning based stuff, artificial intelligence, data mining, big data, and so on, we have moved towards a point where we don't care about parameters, we don't care about assumptions, we don't care about questions, but statisticians have come up with codes, methods that machine in the machine learning, okay, that looks at the data without any assumptions, without any questions, and tries to find interesting information out of it with support. Okay, supportable, provable, or understandable, interesting information. So the role of the researcher is not to make assumptions, come up with questions, decide on analysis, but you just make up the mathematical model that will look at the data, find the interesting things, get it out, and tell you, okay, look, this is interesting, make something out of it. And the statistician does the analysis part, does the machine learning model, lets it into a big data set, and collects the interesting information and tries to make something out of it. This is the new generation of statistics. Right. So that's enough for this week. Watch it again if you have any troubles. I don't know how long it has been, but take notes while you're watching and ask them to me, right? I'll see you next week. Bye.